Okay, the law of refraction is a little bit more complicated, but not terribly so. First of all, when a light travels from a vacuum to some medium, it slows down. All right, so if I have light traveling here, say with a speed equal to 3 times 10 to the 8th meters per second, which is the speed that it travels in a vacuum, and then it comes to some medium. All right, it enters some medium. That light is now going to travel with a new velocity. And so that velocity will equal to something that is less than the speed of light. It will travel more slowly. And we describe this by the index of refraction. N is called the index of refraction, and it's defined as the speed of light in a vacuum which is the bigger value, divided by the speed of light in a medium. The speed of light in the medium being the smaller value. And so, of course, this value for n, since the speed of light in a vacuum is always the bigger number, is going to be greater than or equal to 1. So n is equal to 1 if your medium is a vacuum, because then c and v are the same. Oh, and we can write this also. N is equal to c divided by v, where c is equal to 3 times 10 to the 8th meters per second. Oh, here we go. I'm sorry. The speed of light in a vacuum is 3 times 10 to the 8th meters per second. That number is under the constants part on your equation sheet. Here are some indices of refraction. So notice for gases, air, and helium, their index of refraction isn't actually equal to 1. It's like 1.000 something. But I'll just list them here as 1. And here on out, we'll just assume that when light is traveling in air, it's traveling at the speed of light. However, notice that when you go into liquids and gases, liquids and solids rather, that the speed of the index can be quite high. So if I imagine glass, let's just say that its index is equal to 1.5, and I want to know its velocity. Well, velocity is going to equal c divided by n. And so it's going to be 3 times 10 to the 8th meters per second divided by 1.5, which would be 2 times 10 to the 8 meters per second. So you see the velocity is greatly reduced when it enters this medium. Right. Here's a question. This is a kinematics type question. I'll let you try it on your own. But it just asks, how long does a light take to travel this distance? Remember, for our kinematics, our basic definition of speed is just distance over time. And here I'm looking for the time. So you'll need to find the distance and the velocity of the light in this new medium. Now, the law of refraction also describes how light bends when it enters a different medium. And the law of refraction, this is the law of refraction, excuse me, it says that n1 sine theta 1 equals n2 sine theta 2. Moving from a low to a high index, the ray will bend towards the normal line. So for example, here, if I had light that moves in this direction, it's going to bend in this direction. And then if I'm moving now in the opposite direction, it's reversible. So if I'm moving now from a high to low index, if I'm going from high to low n, the ray bends away from the normal. And there's a simple way. You might not think it's that simple, but I think it's kind of fun. A simple way to think about this. Let me look on the next page right quick. Yeah, a simple way to think about this, something we call the marching band analogy. I'm going to stay here since I have more space. I have this. If you imagine a marching band that's marching along in this direction, you know, each of these, the marching band tries to stay all in, a good marching band stays all in one speed, right? But imagine that my marching band actually enters a muddy field. And you know it's very difficult to march in a muddy field because you get mud stuck to your shoes and you just walk more slowly. And so as this marching band comes along, notice I have this wave front, which is like the wave front of my waves. Well, here, the people that first encounter the muddy field are going to slow down, right, because they're entering this medium, or they're entering this muddy field. But over here, these people are going to continue moving at a higher velocity. So here I'll have a big velocity, and over here I'll have a small velocity. If you've ever driven a twin what's it called, twin rotor boat, that's not the right word, twin prop boat, where you have two engines on the back, or two propellers, you can change the speed of either propeller to rotate your boat one direction or the other. And so the same idea is here, that if I have a higher velocity on this side, it's going to cause the marching band on this side to speed up, and it's going to bend. And so when the marching band comes over into the muddy field, when it finally gets over there, it's actually going to be moving in this direction, having bent its path towards the normal. And so we can think about this in a similar way. As I move along here, my wave fronts, my first wave front to hit this medium will slow down. But over here, this wave front doesn't slow down, so it continues moving at a faster speed, and that will cause the entire wave front to shift over in this direction. And then if I'm moving, let me erase this. If I'm moving instead from a high to a low index, like I am here, imagine my wave fronts. And now this wave front over here, this guy, this band, this is like the saxophone player or whatever, he starts moving faster as he comes out of the muddy field. And so it bends away from the normal. There's a really cool video that a student of mine made. He observed this idea that when you have these different velocities, it can shift your whole wave from one side to the other. He found this was true on his lawnmower, and he shows this nice little demonstration of this where he has the lawnmower. Part of it is going on the grass, and part of it is going on the cement. And so this was Chris Cortez. Most of y'all probably don't know him, but he's a number of years ago. But you can watch that video here. It's kind of interesting, I think. Might help you understand. All right. And then I also have another video here. Well, let's see here. Oh, so a good example of refraction is if you have a straw in a glass, it appears to bend. Like if you look at it from the side, you can take a fork or something and do the same thing, or a toothpick, and it appears actually as if the straw is broken in two. So try that on your own. You can try it at home or wherever. You need a clear glass so you can see it from the side. And then I also have another clip here. This is what happens when you put glass that has an index of refraction that is the same as your medium inside. And so this is fairly interesting. This is from the Spangler Science Network. So I'll leave you to watch these on your own. And then next we will pick up with total internal reflection.